So what should we do if the variables are not independent? Let's go through an example. Consider a sister and brother. We want to find their ethnicity. Uh, we, so what is the probability that the sister is white, given that we know that the brother is also white? So probably it's quite likely, say 90%. But then what is the probability that the sister is white given that we know her brother is black? Well, it's less likely, say for example 10%, knowing that they're from the same parents. Now, from this we can conclude that S and B, the two are not independent, because if they were independent, then this conditional probability of S given B would be, the two will be equal. Like S would not depend on the value of B, whereas here it does. Now, assume that we know their parents. Okay, so then, like here, we know that the parent of the sister is, for example, white. Now, the probability of S being equal to white, given that the parents are white, imagine that it's very high probability, like 95%. Okay? Now, from here, we can see that the effect of knowing the color of the brother does not matter anymore. The probability of the sister being white, knowing that the parent is white, and then knowing that the brother is white is still 95%. And also knowing that the brother is black is still 95%. What matters is really knowing the cause of the skin color of the sister, which is the parents. Knowing the brother does not matter here. And from there we can conclude that S is conditionally independent of B given the parents. And we write it in this form: S independent of B given the parents. Now, let's get back to our COVID example. Here we consider fever and the PCR test result. If someone has fever, we can guess their test result and vice versa. So for example, the probability of someone having fever, given that we know they didn't have a PCR, they had a negative PCR test, say it's 20%. And if we know that they had the PCR test, it increases, because they most likely had COVID, and it is likely that they exhibit some symptoms. So say 70%. And you see that F and P, the value of F equal to 1 does depend on P from here to here. They are not the same. So they are not independent. And the same we can do for P. If we know that the person does have fever or does not, it affects the probability of a positive or negative PCR test result. So the conclusion is that the two variables are not independent. But we don't stop here. We know that now if we additionally know another variable, say that we know the person is infected by COVID, C equal to 1, then they have fever and test positive with and test positive with a high probability. So P of having fever, given that we know the person is infected with COVID, will be 0.6, for example, and say P of having a positive test result, given that the person has COVID, will be 0.9. But then more importantly, what's happening here is that knowing about fever no longer increases the knowledge about the test results, and vice versa. So the probability of having fever conditioned on the fact that we know the person has COVID, it is still 0.6, even if now we additionally know that the person had a PCR test result. Okay? Because the whole role of a PCR test result is to indicate, to reveal if the person had COVID or not. Now we know the person has COVID, so it doesn't change the probability. And we can easily say that regardless of the value of p being equal to 0 or 1, here I'm using 0 and 1 instead of false and positive to just make it easier to read. Regardless of the value, we will have p of f equal to 1, like having a fever, knowing that the person has COVID will be 0.6 as before. Okay. Now, roughly we can say the same with the PCR test result. Okay. If we know the person has COVID, then most likely we will see a positive test result. Okay. And this does not matter if the person has fever or not. Like if the person is symptomatic or asymptomatic, the test is supposed to work here in any case. Okay, so what can we conclude from here? Can we say that f is conditionally independent of p given c? No, we should be careful. We only so far showed that it is conditionally independent of c being equal to 1. What do I mean by that? It means that just knowing that the person has COVID, then we can conclude that f and p are independent. Okay, because for example here f equal to 1 is independent of the value of p equal to 0 and p equal to 1. And by the way, I can easily write down the opposite, like f equal to 0 condition on the same part, because they should add up to 1. If I want to conclude that f and p are independent given c, I need to make to reach the same conclusion, the same equations for c equal to 0 as well. And that's what we aim here in this slide. Now, if we know that the person does not have COVID, it's not infected, then they have fever and will test positive with a low probability. Okay, so fever will be the probability of the person having fever, knowing that the person does not have COVID, will be low, and the probability of a positive test result, knowing that the person is not infected with COVID, is also low. Now you may ask, how do we know? Just for simplicity, assume that we somehow know, like with a very accurate test result, even more accurate than the PCR test, we somehow know that the person is not infected. Okay? Now, we can further conclude that the probability of having fever, knowing that the person does not have COVID, then it does not depend anymore on the PCR test result. So either p equal to 0 or p equal to 1, doesn't matter. It's the same as just knowing the person has COVID, does not have COVID, and it's low, 0.2. And the same we can conclude for the PCR test result. Knowing that the person is not infected is sufficient. We will conclude the probability. It doesn't matter anymore if the person has fever or not. Okay? So we can conclude that f and p are independent given c equal to 0. Now, putting this together with the previous conclusion of c equal to 1, we can conclude that f is independent of p given c. Fever is conditionally independent of the test result given COVID. Okay? This does not, of course, always hold. For some choices of variables, only partial independence can happen here. Like we may have only this part. But here, we reach the conclusion that it holds in general. Good. So let's now try to formalize stuff. Consider the sets of random variables x, y, z. So here x is a set. It can include several variables, and so is y and z. We say that x is conditionally independent of y given z in a distribution P. We didn't talk much about the distribution P. It was implicit in the previous slides. Here we're formalizing it, so we put it here. Denote that P models this notation. X independent of y condition on z. And here we want to define this will hold if P of x given y and z equals to P of x given z. Now, if we want to be precise, we need to write down the values. Of course, we always, for simplicity, almost always we omit these parts of equal to y, z. Remember that the capital X is the variable of interest, the random variable itself. The small letter here, these are the value that the random variable takes. So it is emphasizing that this condition should hold for all values of x, y, and z. Okay. In particular, we saw that like z equal to z and y equal to y, this should always hold, especially for z equal to z, like what we saw here, c equal to 0 and c equal to 1, both need to hold in order to conclude that they are independent. Yeah, they're independent. Okay. Now, just a few side notes. The variable in the set z are said, the variables are said to be observed. So here z is the observed variable. If z is empty, it's not conditioned on anything, then we can go back to our originally defined independence definition. We just say x and y are mutually statistically or probabilistically independent. You can also say that they're marginally independent. And we just say p of x given y is p equals to p of x. The set of all probability independences in P, we denote them by this, we capture it by this set I of P, and well, P stands for the distribution, I stands for independencies. Okay, so I of P will include all such conditional independence that hold in the distribution. For example, in the previous case where we had F, C, and P, then I of P would include this conditional independence, F independent of P given C. And we have a proposition here. We say that X and Y are independent given Z if it holds that X and Y condition on Z is equal to P of X given Z times P of Y given Z. You see, it's a straightforward generalization of the non-conditional case where we just had P of X and Y is equal to P of X times P of Y. What is added here is just that we condition it on Z. So it's easy to remember and it's also intuitive. And you can try to prove this proposition. Now, how can conditional independence help? We just saw that how independence can help, but what about conditional independence? Let's go back to our example. COVID fever PCR test result. We saw a conditional independence. Now, if we write the joint probability distribution of F, P, and C using the conditional probability, we can write it down as P of F given P and C times probability of P and C. Now, we further know that this conditional independence holds. If we knew, by the way, if we knew that P of P and C, if P and C would be independent, then we could easily write down this part as P of P times P of C. But this doesn't hold. What instead holds is that F is independent of P given C. Okay, it is included in the set of independencies. So we know that fever and test results are independent condition on COVID, which we just showed. How can we use this? Well, then by definition, this part, P of F condition on P and C, can be reduced to P of F given C, right? This is right here. Don't get bothered with the notations with these parts X, Y, Z. You can see that this is exactly equal to this, and we just got rid of P because it was independent of it, okay? So what happens to the number of parameters? Well, we have 2 here. It's a conditional probability. We have 2 for C. And we have 4 minus 1, 3 for this one. So 2 plus 3 equals to 5. Okay, original we had 7. And again, the importance of conditional independence. Conditional independence can reduce the number of parameters. Little exercise here, show that the following factorization results in the same number of parameters. So here we factorized according to F. We said it's equal to probability of F condition on P and C times probability of P and C. Now, if we would have done it differently, we had conditioned it on C. Say P of F and P, condition on C times P of C. Go on and try to show that still we would have the same number of parameters. This should be intuitively correct because we're using the same independence, and so we don't expect fewer or more number of parameters. Okay, so far we covered examples. Now how to generalize the idea. First, step one is we need to factorize the joint distribution into CPDs, right? We just saw it in the previous slide. We always do it, this part. And how to do this? Here is where chain rule can help us. The chain rule for random variables. It says that P of x1 to xn, I will read from right to left, it's easier. This joint probability distribution can be factorized as follows. It's probability of x1 times P of x2 given x1 times P of x3 given x2 and x1 all the way to P of xn given xn minus 1 to x1. Okay, and you can write it down in this compact form, P of xi condition on xi minus 1 to x1. This you can prove using the definitions of conditional probability. Okay. Now, just note that sometimes in the literature, this P of x1 to xn is written as P of x1 to x1, xn to x1 to resemble the order of the factorization. Okay, because it starts from x1 to xn, and it may help also to remember it easier. But of course, the two are equal. Doesn't matter. P of A and B is equal to P of B and A. Okay. A little exercise here before we proceed to the next step. For binary valued random variables, compute the number of required parameters using the chain rule. Okay. Like we know here, if they're binary, we know that we need 2 to the power of n minus 1 variables, parameters to model this joint distribution. But then if we now do it using this chain rule, show that the number of parameters does not reduce. I already kind of gave the answer. And here's the hint. And then in the next exercise, you're asked to generalize it for general discrete random variables, where you can have alpha 1 for x1 to alpha n time for xn. Again, intuitively, this is expected, right? Because chain rule holds for general joint probability distributions. We haven't yet done any reduction in these CPD, conditional probability distribution terms, so we don't expect any reduction in the number of parameters. So this was step one, to factorize. Step two, we need to simplify some of these CPD terms, okay? Conditional probability in distributions. Based on what? Based on conditional independencies. How? Okay, here is a little example. Consider joint distribution P of x1 to x4. Using the chain rule, we will factorize it in P of x4 given x3 to x1 times P of x3 given x2 x1 and so on to P of x1. Imagine that we have a conditional independence where x4 is independent of x1 and x2 given x3. Okay, so obviously that means that I can just omit x2 and x1 from this conditional distribution. And this means that the number of required parameters for this CPD will reduce from 2 times 2 times 2, 8, to only 2. Okay. Now the joint distribution becomes, so I will just go from here to here, where I can omit x1 and x2, and I will get this simplified version of the joint probability distribution. And the total number of parameters now reduces from 15, originally I had 2 to the power of 4 minus 1, to 2 plus 4 plus 2 plus 1, which is 9. Okay? We go on with a little exercise. So here we can see that if a conditional independence holds for P, it can be accordingly factorized so that the corresponding CPD term is simplified. Okay? Whatever independence you give me here, I can just, what I need is the term, to have the term P of whatever is here condition on this. This is supposedly a single variable, condition on a bunch of other variables here, and here it will be independent on some other variables. Okay, meaning that this should appear in the factorization, something like this. So I need the first term condition on all the other variables, and then I will simplify it. Now, the term that I just described, I can make sure that it appears in the chain rule based on the reordering. So I can reorder the variables so that the desired term will appear here. So I can always make sure that the single conditional independence will somehow appear in the CPD terms in the factorization, and then I can reduce the number of parameters. Now, the exercise is asking what can be said about the inverse statement, meaning that if I see a factorization that compared to the chain rule, like here, I see that one of the CPDs are reduced, then can I conclude that there is a conditional independence? Okay, good. Now, I want to continue with the example. Imagine that in addition to this conditional independence, we have this additional one, x1 being independent of x2 given x3. So it's no longer about x4. Here it's all about x1, x2, x3. Then we will have that x1 given x2, x3 is just equal to x1 given x3. x2 is omitted. Okay, but we cannot apply this to the previous factorization. This is what we ended up last time. x4 given x3 and the remaining ones. Why we cannot use this? Because I don't have this term here. Okay, x1 given x2, x3. It's the only place where x1 appears on the left side of this conditioning notation is here, but it's not conditioned on anything. So what should we do? Well, we can reorder the variables and then use the chain rule again so that this part is rewritten. Okay, so if I do it in a way that I'm fine with the first part. So originally I had x4 condition on the other variables. That is fine, but here I need x1 condition on x2 and x3. And then the other ones I also don't care. It can be x3 given x2 and p of x2, or x2 given x3 and then given times p of x3. But I need this term. And I need the other one also so that I can still use the previous conditional independence here, okay? So if I do this, then I will simplify this term as in the previous slide, but also I will reduce this one. And then I will end up with this simplified version where two of the CPDs are simplified now. Now note that this way of writing things is, if I want to write it down using the order, it will be p of x2 and x3 and x1 and x4, right here. Of course, this doesn't matter. You can just write down x1, x2, x3, x4. It's just to help with ordering of the CPD terms. Now, what if we additionally have x3 condition independent of x2 conditioned on x1? Okay, so here we had x1 conditioned on x3 being, then it's independent of x2. Here it's x3 and x2. Okay. Now, it is impossible if we want to further reduce, simplify this factorization. You can try yourself, like at least it's not straightforward to do this, because this one requires p of x1 appearing condition on x2 and x3. This one, it requires p of x3 condition on x2 and x1. Okay, so if we want to use our previous approach, at least for sure, we cannot handle both of them in the same factorization. Okay, and the conclusion here, which we will later make it very concrete and rigorous in what conditions it can happen, is that not all independencies can appear in a factorization. Okay? Now, see it in practice. Back to our code example with 12 variables. So what should we do? We should just find the conditional independencies and factorize the joint distribution accordingly. Well, yes, that is the idea, but couple of questions. First, how to find these conditional independencies IP? We need to find them from this data set. I mean, in all the previous examples, I just said assume that we are given this conditional independencies and this conditional independence. But then how can we really find it? And the answer is that we will get back to this in the chapter structure learning. Let's just say that there are statistical tests for doing this. Now, even if we have this I of P, how can we systematically factorize the joint distribution accordingly? Okay, like which ones to include, which of these conditional independencies to include, which ones not, and according to what order. We just saw that we may not be able to include all of them. And like a visualization tool can help here, like a graph. And this is the whole idea of Bayesian networks, okay, which we will get back in the next video. Just to summarize, the goal was to find from data the joint probability distribution. Here's the data, and we wanted to get the joint probability distribution. I want to make it more concrete by saying, well, the goal is to find the correct factorization of the joint probability distribution. What do we mean by correct? Let's put that aside for now. But let's just say that each factorization will result in a certain number of parameters. Okay? The whole purpose of Bayesian nets is about this factorization. That's what's happening behind the scenes. Okay? And we want to find, like, each factorization can result in a different number of parameters. We want to find which one is correct. And how can we do that? Well, first of all, we need to find I of P, which conditional independence hold. For example, if we perform those tests that I told you, like imagine that we find that I of P will have C conditional independent of D given M, okay? And also M is independent of D. Then how can we factorize this? So the next question is how and then if we know IP, what should we do? We will cover in the next video.